All right, my bad. Let's get started. Okay, so yes, today we are going to be talking about a third way to calculate enthalpy. Okay, so just to remind you, this week we've introduced, actually I think it was the end of last week, we introduced how to calculate enthalpy using that thermodynamic standard page. And then this week we said, okay, well we got this added complication if we have an aqueous reaction, right? If we have an aqueous reaction, because those ions dissociate and not all of them are participating in the chemical reaction, some are just spectator ions, we have to use our net ionic equation and look up the reactants and the products using that net ionic equation. And then we introduced Hess's law, which is kind of this pain in the butt way that we can combine reactions that we know about to figure out a reaction that we don't know about and figure out its change in enthalpy. And it was kind of this long drawn out way, but again, it was really theoretically important because anytime we're using that thermodynamic standard page, we're really using Hess's law. We kind of simplified things down to use that page, but it's really using Hess's law and those formation chemical equations. And now we're going to talk about bond dissociation energy. All right, this is another way where we can calculate the delta H of a reaction. Bond dissociation energy is the amount of energy that you have to put in order to break a chemical bond. All right, it turns out that it's also the same amount of energy that's released when a chemical bond is formed. So in chemical reactions, we're always making and breaking bonds. To break bonds, you put energy in, and when new bonds are formed, you get energy that's released, okay? And this bond dissociation enthalpy is a really important, bond dissociation energy is kind of a really important theoretical thing in the sense that this is where enthalpy comes from, right? We talk about the enthalpy of a chemical reaction. Well, where is that heat coming from? Remember at the very beginning, we made this analogy to energy in physics, potential energy and kinetic energy, and how you can convert potential energy into kinetic energy, right? And we said in chemistry, we don't really deal with those two quantities, but what we deal with is chemical energy, energy that is stored in chemical bonds. And that can be transferred into thermal energy, amount of heat that is released, right? So this bond dissociation energy, this is what we're talking about. This is the energy that is stored in those chemical bonds. You got to put energy in to break them, but when new bonds are formed, energy is released. And that's how a chemical reaction works. All right, so this is how we're going to kind of think of a chemical reaction from an energy standpoint. We're going to make this little graph here. Let me actually make this a little bit bigger. All right, we have this y-axis of increasing energy, and we're going to start here at this energy level, which is where our reactants are. All right, we're going to have to put energy in order to break the existing chemical bonds in our reactants. So break bonds, that means we're going to input energy. All right, so now we're up here where all of our reactants have had their bonds broken. But now our products are going to start to form. And when our products form, we get a bunch of new bonds that are made. And when those new bonds are made, this is going to release energy. So bonds breaking is an input of energy. Bonds forming, that releases energy. All right, so now I'm down here at the energy level of my products. All right? And then this gap right here, this gap between the product side and the reactant side, this is my delta H of my reaction. In this case, when those new bonds were formed, I released more energy than I had to put in. So specifically here, this would be a chemical reaction that has a negative delta H, which we call what kind of reaction? exothermic. All right, if instead we did this same game here, all right, we put in a bunch of energy in order to break all those bonds, and then our products started to form new bonds. But we had to put more energy in than was released when those new bonds were formed. Again, this is going to release energy. All right, well now, this reaction required a net input of energy. So this would be a positive delta H, or an endothermic reaction. Okay, and so when we're doing this here, just like our analogy between potential energy and kinetic energy in physics, we have this analogous type of energy that's chemical energy, where the energy stored in chemical bonds. And when we do a chemical reaction, that energy can be transferred into our other type of energy, thermal energy, being released by our chemical reaction, or absorbed, depending on whether we have to put in more energy to break bonds, or whether more energy is going to be released when new bonds are formed. Okay? Cool. All right, so let's take a look at some bond dissociation energies. All right? We have this chart here. What this chart is telling me is, for example, with a carbon-carbon bond, it requires 348 kilojoules to break a mole of carbon-carbon bonds, right? This is also telling me that if I made a mole of carbon-carbon bonds, it would release 348 kilojoules of energy. Okay? So, what can we do with this chart here? What we're going to do is we're going to take a look at a chemical reaction. Oh no, that's not what I want, sorry. Okay. But we're going to need a little bit more information than just our chemical equation. So what we're going to do is we're going to look at the Lewis structures of our reactants and our products. All right. So H2 is two hydrogen atoms with that covalent bond between them. Cl2, same sort of thing, but these chlorines have those lone pairs. And in this chemical reaction, I'm going to create two new molecules of HCl, hydrogen chloride here. Okay? These Lewis structures, you might remember them from Chem1AFA24. Importantly here, what we've been doing up until this point in this course is we're just reading them, right? So if we've been given one, we should be able to know what we're looking at in terms of what those sticks are and what those lines are. We haven't sort of formally introduced how to write them ourselves, all right? So how did I come up with this? We'll go over that later in the course. But right now, you just need to be able to read these structures. Again, these are covalent bonds. That's a shared pair of electrons. These are lone pairs, just kind of chilling on that particular atom. All right, and what we need to do is we're going to play this game where you're going to tell me which bonds have been broken over here on our reactant side and which new bonds have been formed over here on the product side. You're going to play the spot the difference game here, right? What bonds do I not have on the product side that were there on the reactant side? What new bonds do I have on my product side? Does anybody see a bond that was broken in this chemical reaction? The hydrogen-hydrogen bond. Boom. And what's another one? The chlorine-chlorine bond. All right, and what new bonds do we have on the other side? Both of these HCl bonds. All right, in this case, it was pretty straightforward. Those are the only options. All right, well, let's do a little bit more complicated of an example later. Cool, so now I'm gonna figure out how much energy I had to put in to break these two bonds. All right, so I'm gonna go to my chart here. According to my chart, that hydrogen-hydrogen bond is going to require 436 kilojoules to break. That chlorine-chlorine bond is going to require 242 kilojoules to break. So I'm going to have to put in that much energy in order to break those two bonds. But when my new bonds are formed, I'm going to get a bunch of energy back out of this, right? I'm going to get a bunch of energy released. I'm going to get 2 of those HCl bonds formed. So this one's going to release 431 kilojoules. This one's going to release 431 kilojoules. All right. So then to calculate the delta H of this reaction, okay, let's think. If we have to put energy in, is that a positive value for energy or a negative value? These bonds have to absorb that energy. So is that going to be positive or negative when it absorbs energy? So our choices are absorb or release, right? Which one corresponds to our negative sign? That's what we want to think about. So the absorbs means we have to input energy. When new bonds are formed, that releases energy. So that's going to be negative. Okay? So our formula here that we're going to use is our the sum of the bond dissociation energy of our bonds that we broke. And then we're going to subtract, so they have that proper negative sign, the sum of the bond dissociation energy of those new bonds that were formed. So broken minus formed is what we're going to have to remember here. Okay? Real quick, when we were using this chart, what do we say to ourselves? What minus what? Products minus reactants, right? That's how we made sure to keep our things straight here. We took our product side minus our reactant side. Products minus reactants, okay? Here, we're going to have something different that we chant to ourselves. We're going to chant to ourselves, broken minus formed. All right, and you should go back to that logic that we just did with our signage here. That's how we got that formula to begin with, all right? But broken minus formed. What's up?
BD is bond?
No, BD is the bond dissociation energy from that chart. Okay, cool. So using this chart here, I guess we grabbed these values, put them above these bonds here. Everybody take a second and use that formula and calculate the delta H of this reaction. right, we get a delta H of our reaction of 134 kilojoules per mole. All right, so what would we say about this reaction here? Is it endothermic or exothermic? Exothermic. All right, and that's because I had to put in less energy than was released in this chemical reaction, right? I had to put in energy to break bonds, but I got out more energy when those new bonds formed on our product side. Cool. All right, let's do another one here. Let's see if I can do this without breaking this. Oh, cool. All right. All right. So again, we need a chemical reaction. We need to look at some Lewis structures here. I lied. We're going to do one thing first. Before we go on here, let's take a look at a few specific entries here. Let's look specifically at a carbon-carbon single bond compared to a carbon-carbon double bond compared to a carbon-carbon triple bond. Okay? So, which one of these is going to require more energy to break? A single bond, double bond, or triple bond? Triple bond, and that is always the case, right? Triple bonds are stronger than double bonds, which are stronger than single bonds, okay? But importantly, let's look specifically at these numbers, and let's do 2 times a carbon-carbon single bond. All right, if we multiply that carbon-carbon single bond number by 2, that 348 times 2, we get 696 kilojoules per mole. Okay, so how does that compare with a carbon-carbon double bond? Right, it's less. So it turns out that yes, you get when you add that extra bond, it does get stronger, but it's not quite as strong as that initial carbon-carbon bond, right? That first bond is always the strongest if you have a multiple order bond, okay? So that's going to be really important in this next example here, all right? We got to keep that in mind. Cool, all right. Now we're going to take a compound with a carbon-carbon double bond. All right, and we're going to react this thing. With hydrogen chloride. All right, this is one of the reactions you would cover in organic chemistry, what's called an addition reaction. All right, and what happens is that double bond gets changed to a single bond, and the hydrogen and the chlorine gets added to either side. Fun fact, you all don't have to know about all that. Okay? What you need to do is, given a structure like this, given a chemical equation with these Lewis structures, you need to go in and tell me what bonds are broken and what new bonds are formed. I think I mixed my colors up. All right, so let's look here. Does anybody see a bond that needs to be broken? Right, yeah, so I have this carbon-carbon double bond. I got one of them that we need to break here. And what else do I need to break? This one over here. Okay? When I go to my other side, what new bonds are being formed? The carbon-hydrogen and the carbon-chlorine. The other bonds, all of these, are the same on both sides, so I'm going to ignore them. Nothing changed there. Okay? And this is indeed what happens in this chemical reaction. This second bond here is what's reacting. But the problem is that we can't use our chart for just one of these two double bonds. All right, so instead what we're going to do is we're going to imagine that both of these bonds right here get broken. And then on my other side, I'm going to reform that carbon-carbon single bond. All right, so we can't break just one of those bonds, so we're going to break them both, and we'll just make a new one over on this side. Okay, at least mathematically, that's what we're doing. So then everybody's going to take a second and use this chart and tell me what the delta H is of this reaction. And what are we going to chant to ourselves? Everybody already forgot. Broken minus formed, all right? Cool. All right, so yeah, everybody take a second. Tell me what the enthalpy is of this reaction here.
Can you zoom in a little bit?
Sure. All right, I'm going to look these up. I'm again going to form a new carbon-carbon single bond along with my carbon-hydrogen and my carbon-chlorine. Punch that into my calculator. Again, we're going to do the broken minus the formed. All right, and again, I'm sort of putting this second term here in parentheses to be really careful with my order of operations and specifically making sure this minus sign gets distributed in correctly. All right, so the delta H of this reaction is negative 44 kilojoules per mole. Another exothermic reaction. Oh, hold on. I effed that up. 438. My bad. 438. 328. Did I copy that wrong? Oh my gosh. Okay. Whoo. Okay. 413. Oh yeah, that is what it was. 348. So wait, was I right? And then 328. 340. Holy cow. Oh, the negative 44 was right? Holy hell. Yeah, negative 44. Okay, I'm sorry. I punched it into my calculator correct, wrote it on the page wrong, then punched it into my calculator wrong.
Yeah,
Yes.
one of them up there is transposed. The one on the carbon to carbon should be 348. But you have it written right down in the parentheses.
Right, okay. I see what you're saying. That is the initial point of error. Glad we tracked that down. Okay, my bad. Okay, so anyways, yes, negative 44. If you punched these correct numbers now that I've written it down correctly into our calculator here. Cool. All right, so again, we can calculate our enthalpy change using this bond dissociation energy. And again, this is kind of important because this is where we want to think about where enthalpy comes from. Why do chemical reactions release thermal energy? Well, that was energy that was stored in those chemical bonds, right? Or why does a reaction absorb thermal energy? Well, it's got to in order to break the bonds on the reactant side. And you don't get quite as much energy out when new bonds are formed on your product side, right? So this bond dissociation is another way of calculating that delta H. But importantly, this is how we want to think about enthalpy and where it comes from. All right, cool. So last thing we're going to do is talk about what's called reaction calorimetry. All right, and what we're trying to hammer home here is we've been calculating these enthalpy values, calling them enthalpy, fantastic, right? Well, importantly, that is the amount of heat that is released or absorbed by a reaction. And we want to think about that. What does the heat do? Is it raises the temperature, okay? So this is how we're going to sort of combine our discussion of calorimetry with our discussion of enthalpy. So we need a sample chemical reaction to play with here. All right, we're going to take HCl and NaOH. This is our acid-base reaction. This is the last of our solution reactions that we need to cover here because we've reminded ourselves of single replacement reactions and precipitation reactions. These acid-base reactions are also aqueous solution reactions. All right, so when we get our balanced chemical equation here, before we can look this stuff up on our standard enthalpy page, we need our net ionic equation. All right, so everybody take a minute and get the net ionic equation that we have here for this chemical reaction.
I found this on the web.
No, not you. All right, so I take my aqueous compounds and I split them up. Hydrogen ion, chloride ion. Aqueous compounds, split it up. Sodium ion, hydroxide ion. Aqueous compounds, split it up. Sodium chloride. And now I have my liquid water, which I'm not going to touch. I'm just going to copy and paste it down exactly as it is above. All right, so you only split up the aqueous compounds. If it's anything else, copy, paste. Don't add charges, don't do anything. And now I'm going to cross out what's on both sides here. What are on both sides of our chemical equation? The sodiums and the chlorides. So my net ionic equation is H plus AQ plus OH minus AQ gives us H2O in that liquid state. Cool. All right, and of course we're going to have to need the enthalpy of this equation here. This is our enthalpy week. So we're going to go to that standard formation enthalpy page and look up our compounds. All right, we're going to need to look, oh look, there's one of them for you. Hydrogen ion. Okay, turned out that our standard enthalpy of a hydrogen ion is just 0. The other two will be in this section here. So everybody take a second, grab those relevant values, and then tell me what the change in enthalpy is for this acid-base reaction. See if I can punch them into my calculator correctly. Cool. All right, so to be clear, the ones that I'm going to need are that hydroxide ion standard enthalpy and liquid water standard enthalpy. Remember, that's only that first column that we're paying attention to. All right, so hydrogen was 0. Hydroxide was the negative 230.02. And that liquid water, negative 285.8. All right. And again, now we're back to our standard enthalpies, so let's not get confused here. We always chant to ourselves, products minus reactants. So my delta H is going to be that, of this reaction, is going to be that negative 285.8 minus my sum of my reactants. Hydrogen is just 0. And my hydroxide's 230.02. So our delta H of this reaction is negative 55.78 kilojoules per mole. How many sig figs should I have on that number? Rather, how many decimal places, since this is addition and subtraction to the tenths, right? Just 1. I'm going to be limited by that first value here. Now, since I'm going to go on and do more math, I'm not going to round this number, okay? This is just kind of, we needed this chemical reaction as a sample here. And it's an exothermic reaction. So what we want to do is kind of think about what exactly is happening when this reaction takes place. All right, so let's make a beaker, because of course this was an aqueous reaction. So these molecules are floating around next to a whole bunch of what type of molecule in an aqueous solution? Water, right? In any aqueous solution, yes, the sodium, the hydroxide, the hydrogen ions, the chloride ions, they're all there. But importantly, there is a crap ton more water molecules floating around in this system. Okay? And this is what we call our solution. What happens is these hydrogen ions, they combine with these hydroxide ions, and they make those water molecules. This is what we call our chemical reaction. And we said that this chemical reaction was exothermic. So when those new bonds are formed, this reaction is going to release a whole bunch of thermal energy. And where is that thermal energy going to go? It's going to be absorbed by that surrounding solution. All right? So, according to our first law of thermodynamics here, this thing coming back again, we have to have this conservation of energy, which says that every bit of energy that is lost by my chemical reaction, where is it going to go? It has to go into the surrounding solution. So the sum of those two terms have to equal 0. All right, that's what my first law of thermodynamics says. Any amount of heat that is lost due to that chemical reaction doesn't just disappear into thin air, it's going to be absorbed by those surrounding solution, those surrounding water molecules. And when those surrounding water molecules absorb that heat, their temperature is going to go up. All right? Cool. So let's take our sample reaction here. With its standard enthalpy. Of negative 55.78 with my sig fig marked. All right. So let's say if 0.38 moles of NaOH are consumed, how much thermal energy is absorbed or released? All right, so this is what we learned how to do last week with our enthalpy stoichiometry here. All right, we have our standard enthalpy, but our standard enthalpy is given to us in kilojoules per mole of reaction. In this reaction here, I don't have 1 full mole, I just have 0.38 moles of my hydroxide being consumed. So in order to get my standard enthalpy, I'm going to take that 0.38 moles of OH, and I need to multiply it by that standard enthalpy, but I'm going to be good with my units here and first convert from moles of hydroxide to moles of reaction. How did I know that it was 1 mole of hydroxide per mole of NaOH? Really, as we established with our net ionic equation, it's really the hydroxide doing the work, but nonetheless. All right, according to my balanced chemical equation, how did I know that it was 1 mole of sodium hydroxide per mole reaction?
Wait, is that first part supposed to be?
Yeah, it doesn't really matter, but yes. Sorry. Thinking, what's it called? Organic chemistry brain here. All right. So I have my 0.38 moles of sodium hydroxide. I'm going to be good and convert from moles sodium hydroxide to moles reaction. Okay, so again, how did I know that it was 1 mole of sodium hydroxide per mole reaction? Because of my stoichiometric coefficient here. Remember, when you draw your balanced chemical equation, you're saying this is what 1 mole of reaction is. So whatever your stoichiometric coefficients are, that's how you're going to convert to 1 mole of reaction. Now I can multiply by my standard enthalpy. 1 mole reaction is negative 55.78 kilojoules. And again, we said that number only has 3 sig figs. So I punch this into my calculator, I get negative 21.1964. What are the units on that number? Kilojoules, right? Because the moles have now canceled out. So was thermal energy absorbed or released according to this calculation? Released, right? Okay, so what did we just calculate here? Again, that's what we're going to call our Q reaction, the amount of heat that was lost by that chemical reaction. Okay, we'll be good. Our sig figs here, we have 3. Oh, no, we don't. We only have 2. All right, so now we're not done here. We're going to ask, what is the Q of our solution? Exactly, right? So because of that conservation of energy, we had that equation, Q reaction plus Q solution equals 0. Well, the only way that I'm going to make that number 0 is by adding positive 21.1964. So if my Q reaction is negative, my Q solution is going to be positive 21.1964. All right. Cool. So what we just established is we know how much of this chemical reaction occurred. We know that this reaction lost a bunch of thermal energy. Where did it go? Well, it had to have been absorbed by the surrounding solution. So we calculated just how much thermal energy that solution absorbed. Cool? But wait, there's more. Okay? We have this calorimetry equation here. Which relates the amount of heat that is absorbed to the heat capacity, the mass, and the change in temperature of that solution. All right, so let's take that same value here and ask ourselves if the solution has a mass of 1,200 grams, what is the observed change in temperature? All right, and what we're talking about here is our solution. So our Q solution is related to the heat capacity, the mass of that solution, and the delta T of that solution. All right, what are we trying to find in this problem here? We want our delta T, okay? We have our Q solution, that's what we found in our previous step. Do we have the mass of this solution? All right, cool. So then what about the heat capacity of this solution? All right, what are we going to, we don't really know for this particular solution, all right, but we can well approximate it based on the fact that this is an aqueous solution. And an aqueous solution is made mostly of water, all right? So the heat capacity of our solution is going to be equal to the heat capacity of water at 4.184 joules per gram degrees Celsius. Now, this is a bit of an approximation. It's a pretty dang good approximation. It actually gets worse the more concentrated your solution is, but for dilute solutions, this is a perfectly great approximation to use. And importantly, this is what we're going to use. So boom, mark it down. All right, cool. And this is because it's aqueous, correct. If it was an alcohol-based solution, we would use the heat capacity of an alcohol. All right, cool. So given what we established previously, that our Q solution is this 21.1964 with only 2 sig figs, and now we have our calorimetry equation here, everybody's going to take a second and calculate the delta T of this reaction. All right, let me just plug this in first. All right, so I have my Q solution. That positive 21.1964 kilojoules is equal to my heat capacity, that 4.184 joules per gram degree Celsius, times the mass, which was 1200 in our problem, times what I'm trying to solve for, that delta T. All right, but before I can do anything, I got a units problem here. All right, what is my units problem? I got kilojoules on one side and joules on the other, and I need these to cancel out because I'm going to be left with the degrees Celsius, delta T. So we're going to have to square them away here. It actually doesn't matter which side you would square away. I'm going to square away my kilojoules into joules by remembering that 1 kilojoule is 1,000 joules. All right, now I can solve by dividing both sides by that 4.184 and that 1,200. Okay, and I get a delta T that is positive, which makes sense because this solution absorbed thermal energy. So I get this value of positive 4.221717 degrees Celsius. And I'm going to be good and round to my 2 significant figures here. All right, so when this acid-base reaction occurs, the heat that reaction loses is absorbed by that surrounding solution, which increases the temperature of that surrounding solution by 4.2 degrees Celsius. Cool? All right. So one more thing that we can do, which is kind of basically the reverse of this problem. To be clear, I gave you information about what chemical reaction you had and how much took place, so you were able to find your Q reaction. That led you to be able to find your Q solution, and then you can use that calorimetry equation to, for example, solve for your change in temperature, right? Now let's say that we have an unknown reaction here. We've carried out this chemical reaction where we're going to look at our net ionic equation here. We've taken this ion and precipitated it out with this ion to form this solid product. One of our aqueous reactions here. All right, according to my charges, my formula's got to be XY2, which means I'm going to need to balance this. All right, so we're going to carry out this precipitation reaction. Is carried out in 650 grams of solution. The temperature decreases from 24.6 to 16.9 degrees Celsius. All right. So if 0.25 moles of Y is consumed, What is the delta H of this reaction? All right, so I'm going to carry out this unknown reaction here. And what I'm going to do is exactly what y'all did in lab, which is to measure the change in temperature that occurs in that solution. And what we're going to do is we're going to work backwards and figure out what the enthalpy is of that chemical reaction. All right? Again, according to that first law of thermodynamics, whatever that reaction has, in this case absorbed, since our temperature went up, where did that heat come from? Well, it had to have come from our solution. Those two were going to have to equal 0, according to that first law of thermodynamics. And given this problem here, which one of these am I going to be able to solve for? I don't have my delta H of this reaction, so I can't get my Q of my reaction. But instead, what I have is all the information that we need for our calorimetry equation here. All right, and that's what's going to help me figure out what happened with that. So like, what the heck is going on with this solution when it decreased in temperature? Well, it had to have lost thermal energy, and this calculation here is going to help me figure that out. All right, again, we have an aqueous solution. It's a precipitation reaction, so we get to use that heat capacity of water. We have the mass of our solution given to us in this problem, and we have our delta T, everything we need to calculate Q solution. All right, so everybody take a second and tell me, what is Q solution in this problem? All right, so I'm going to punch this into my calculator here. And actually, I'm going to be good and do this subtraction problem first, because that'll cut me down to 2 sig figs. I guess I have 2 in my mass as well, but nonetheless. Punch this into my calculator, and I know everybody's response was, holy cow, what is this gigantic number that I have? That doesn't look right. All right. Well, let's think about why this is. What are our units on this value here? Grams cancel out, degrees Celsius cancels out, so we're in just units of joules. And remember, we usually express these quantities in kilojoules, because they're quite a few joules here. All right, and so that's what we're going to do, because eventually we want our delta H in kilojoules per mole. So we're going to take this, convert it to kilojoules. All right, to be clear, I just divided it by 1,000. Okay, cool. So then everybody take a second. If we have our Q solution, what's our Q reaction? Positive 20.9 with its 2 sig figs. Kilojoules. All right, so this is the amount of heat that reaction absorbed. When this precipitation reaction, the temperature of that solution dropped, where did that thermal energy go? Well, it went into helping carry that chemical reaction out. All right? So, we're not quite done though, because this problem asks me not just for my Q, but my delta H. And let's think here, what are the differences between the units in Q and delta H? Q is something that we just report in units of energy, right? But H is special. It's not just units of energy, it's kilojoules per mole reaction, right? So in order to get my delta H here of my reaction, I need to take my Q reaction and I need to divide that by how many moles of reaction occurred. Okay, so given what we just calculated, again, that Q reaction is positive 20.94 with 2 sig figs. All right, and what we said was in this chemical reaction here, 0.25 moles of that anion were consumed. All right, so everybody take a second and tell me, what is the enthalpy of this reaction? All right, so in order to get my standard enthalpy here, my delta H of this reaction, I need to take that value for Q and divide it by moles reaction. All right, now I got to be careful because I had that balanced chemical equation and my problem told me how much of that anion was consumed, but I got to use that balanced chemical equation, that stoichiometric coefficient of 2, in order to convert to moles of reaction. Right? When we drew our balanced chemical equation, we said that it took 2 moles of that anion Y to do 1 mole of reaction. So the delta H of this reaction here is going to be positive 167.527. And now my units are those units for delta H, kilojoules per mole reaction. How many sig figs should I have? Just 2. All right, so we're going to report our delta H to our correct number of sig figs, or 170 kilojoules per mole. So now we had an unknown reaction here. So we can't just look up these things on our standard enthalpy table and figure out what the delta H is of this reaction. So instead, we're going to do a calorimetry experiment where we take some solution and we measure the change in temperature that occurs when a certain amount of this reaction occurs. From that change in temperature, we can figure out our Q solution, the amount of heat that was absorbed or released by that solution. And using the first law of thermodynamics, that will allow us to calculate the Q of that reaction, right? How much heat was absorbed or released by that reaction. And then using the fact that we know how many moles of reaction occurred, we can figure out what the delta H of that reaction is, all right? This is exactly what you would be doing in your post-lab report this afternoon, right? What did you guys do in the lab this week? You performed a chemical reaction and you measured a change in temperature. And what you're going to do is you're going to work backwards from there, just like we did here, to figure out what the change in enthalpy was for that reaction, right? In your case, you knew what the reaction was, so what you're going to do in your post-lab is also go look it up and compare it to that literature value. Cool. All right, that's all I got for y'all. Break.